And we are once again finding our center. What we will be doing this time is finding the center of, again, a two-dimensional object, but this time instead of it being a rectangle with the y stays constant, we're going to find the center of a triangle, so something that has a y equals a particular formula. So what we will be doing, finding the center of a triangle. If I only had a triangle, some sort of visual that we could use to see what a triangle is. Oh yeah, it's right there. That's a teacher who cares, huh? So that will be the object we find the center of, is that particular triangle. Okay, so what I will do is the same thing I did with the rectangle, and that is draw the shape and then basically make a graph. So this then is our y-axis. There's our x-axis, and that is the triangle that you see there made out of wood. So that triangle then has an L and it has an H. And what I will do is, again, the same thing we've done before. We're going to find our X center mass. I'm not going to worry about a Y center mass for this anymore. We're just going to deal with our X's. Yay. So what I'm going to do is the same strategery. I'm going to slice up this triangle into a whole bunch of little tiny slivers so that when I add up the tiny little slivers, I will get the whole object. So that little piece right there, I will call a differential mass. It is also a differential area. All right, same thing we said before. Now this then is the equation of a simple line, right? Well, here, I'll get to that in just a bit. So anyway, what you guys know from the last video, this is a two-dimensional object. So if it's two dimensions, we're going to end up using a sigma. So this is a sigma is a mass of the whole thing divided by the area of the whole thing. The mass whole divided by the A whole, which means it's going to be the same if I break it into small differential masses and small differential areas, right? So it doesn't matter how big of a piece of this object I have, it will maintain the same density. So again, what we'll say is, if I were to ask you what the differential mass is, you would say it's a sigma times a differential area. So this is a sigma times a differential area. Okay, now that differential area is what we will talk about in the previous video. It was the any given area is actually a base times a height, right? A thickness. So the base is how thick is this little tiny sliver, and that's a differential length, isn't it? A dl or a dx is probably what I will call it, a dx. An infinitely thin sliver between 0 and L. I'm going to call it dx. And remember, it's that times a height, right? In the previous video, that height was a constant, wasn't it? It was just whatever it was, because it was a rectangle in the previous video. So now what I need to remind us is a height, the letter H, is nothing more than a Y, isn't it? So that height is nothing more than a Y. So it's a differential thickness times a height. But that height changes, doesn't it? That Y, that height is changing as a function of X, isn't it? So we need something to tell us what Y is in terms of X, don't we? I need an expression. I need a Y expression for the Y in terms of X. Since this is a line, I'm calling it MX plus B. since it starts at the origin, the b will be 0, and the m is the slope, right? So the slope of this line is the rise, which is the capital H, divided by the run, which is the capital L. So what I'm going to call this y is h over L, big H over big L, because it's the height of the whole object divided by length, times x. That's mx. That is equal to y, isn't it? So my differential mass is sigma times the differential area. That differential area is a base times a height. So that height then is nothing more than a y, and the y is an mx plus b. The b dies, the m is simply h over lx. So what I will end up having a swapper tuna dm here in just a bit. My differential mass is nothing more than this sigma times a differential x times all of this right here, h over lx. That's what differential mass is, and I'll actually rewrite it because the dx is the only thing that changes. But remember, our differential mass is the density times the differential area. The differential area is the differential base times that differential height, which means the height at any given instant. It's a function of x. Okay? That's the area. Okay? Differential mass, sigma times that differential area. So again, our formula for our x center mass is 1 over the mass of the whole thing times the integral. We're going to go from 0 to L because we're only integrating along the axis, and it is going to be our x times our differential mass. That formula hasn't changed of all of these videos. So what we will end up doing is having our swapper tuna dm. That differential mass is what we went through all the fuss of writing down over there. So this will end up being 1 over m times the integral from 0 to L x. Now where that dm is, I'm going to write sigma. I'm going to write the h over L first, x, and put the dx on the end. Sigma h x over L times my differential x, my base. Okay? So all of that then is what we will take the integral of in terms of x. So we can fish out all the constants. Remember, you can fish out constants. That piece of wood, it has a set height, it has a set length, it has a set density. So all of what I'm circling here is a constant. I'm going to fish that out. So what I end up having is 1 over m times sigma h over L. Then I will integrate from 0 to L x squared dx. And that's it. This becomes x to the third over 3. Okay, remember. Well, I'll just write it like this again. Sigma h over m L. That's just everything that's outside of the integral now. This will become x to the third over 3, and I will go from 0 to L. Okay? Now, remember, this mass, remember the swapper tuna mass that we did before? The same swappertunity is going to happen again. That mass is the same thing as the mass of the whole object, which means it's a sigma times an A whole. The mass whole is the density times the A whole, right? So that mass whole down here, I'm going to rewrite in what it will end up looking like is I will rewrite the sigma h in the numerator divided by that m now is going to be a sigma times an area, and then that L here needs to go there, right? And there will be one other swapper tuna A I want you to remember. That's the area of the whole thing. The area of the whole entire object. Well, this object is a triangle. What you guys all know the area of a triangle is 1/2 of the base times the height, isn't it? So 1/2 base height, what that means is 1/2 of L times H. So where that A is, what I will end up calling it is 1/2 LH. That's what our area is, the area of the whole darn thing. All right? And that then gets multiplied by, when I put this bound in, it will be L to the third over 3 minus 0 to the third over 3. So that whole expression right there will be multiplied by L to the third over 3. So to rewrite this here, I'll go up here and combine all of this into one expression. It becomes sigma h, that's this numerator here, times L to the third. It will be divided by this sigma times this area, which we called 1/2 LH, times that L times that 3. Okay? So what we'll do is simplify things. Let's kill things that need killing. The sigmas die, the h's die, that L and that L kill 2 of those 3 L's. And what I'm left with is 1/2 in the denominator, a 3, and an L right there, right? So this is L over 3 over 2, isn't it? Which means I can flip, and it ends up being 2/3 L is our XCM is 2/3 L, and we have just found our X center mass of a triangle, provided it starts at the origin. So it's going to be 2/3 of the way over here, which makes sense because this object is very, very heavy on the right. There's a lot more mass here than here. So the center is going to be 2/3 of the way over. It's going to be right there somewhere, 2/3 of the way, maybe right there somewhere. All right. And by symmetry, you guys all know if I just flip this over and say, well, where's the Y center mass? You can say, well, gosh, if the X center mass is 2/3 of the way that way, because it's heavy on the right, can you tell this object is also heavy on the bottom? This is a very bottom heavy item, so it'll be 1/3 of the way up or 2/3 of the way down from there. So if we did it on a y-sis, we would end up just solving it that way. But we're only concerned about our X center mass for shapes that are a little more complexated. 2/3 of the length of that object when you're a triangle. So there's going to be one more example I give you in this list of finding our centers, and that's when the line isn't straight, it's just a curve, but you already know how to integrate those. It'll just be an exponential type of curve. So anywho, there's that. We have found the center of a triangle. So once again, namaste and yay physics, and bye.